So this is actually just kind of a corollary to our little theorem. So our little theorem was if we have an orthonormal matrix and we take its transpose, multiply it, we get the identity. And we know that that means that if Q is square, then the transpose is the inverse, right? So let's think about projecting real quick. So what if I project? What was a projection matrix? You guys remember?
Yeah, it's A times A transpose A inverted A transpose
You guys remember this matrix?
Yeah.
But this is our projection matrix. This projects onto what?
Onto the
multiple columns of A.
Good. So we recall projection matrix. This projects onto columns of A. Kind of motivating question. This is an interesting letter to use. Question? Q? What if instead of projecting onto the columns of A, I was projecting onto the columns of a matrix Q? You guys see that? So what if I was projecting onto an orthonormal set instead of just onto a linearly independent one? You guys recognize that question? So if I was projecting onto a set Q, then I'd be formulating my projection matrix, right? My projection matrix would be, well, it'd be Q, and then it'd be Q transpose Q's inverse times Q transpose.
the inside is just I.
Yeah, and that part's the identity, so it's Q times the identity matrix's inverse times Q transpose.
And that's all Q or I. I mean,
Yeah, don't think too hard about the identity matrix's inverse, right?
that's all I.
The opposite of let's see, the way in which you undo doing nothing is you do nothing, right? So I get Q transpose out of this thing.
Oh wait, it is I.
And then please note, you know that Q transpose Q is the identity. You do not know that Q transpose is. You guys see that? Why would I think those might be different?
Order matters in matrix multiplication.
Good, yeah. First pass, order matters in matrix multiplication. I shouldn't expect things to commute. These things are special though. Like, why don't they commute?
Well, we haven't tried it.
Yeah, we could try it. Sit down and try to construct this same proof. You'll realize that you're going to come up with something weird because you don't know about the rows of Q. Right? I know the columns of Q are a linearly independent set. I don't know anything about the rows.
Well, linearly independent.
Or sorry, not linearly independent. I know they're orthonormal set. But I don't know anything about the rows. Can you guys give me an example of a matrix that has orthonormal columns that doesn't have linearly independent rows?
Would it be like I, but like with something augmented onto it? Like a
Go the other way. So instead of adding stuff to the identity matrix, take stuff away.
Oh,
Just knock off a bunch of places, 0 and 50.
okay, yeah.
So I just want to, so this is what's going to be called a counterexample, right? So I'm going to make a counterexample to the idea that Q transpose is the identity matrix. This is not in general true. Let me read. It scares me to write things down on the board that aren't true. You guys with me? This is not true. The reason I know this is not true is I can make a matrix Q like this.
Oh.
You guys see this? This has linearly independent columns, because it has one non-zero column, right?
Yeah.
But if I take Q times, and I know, right, that if I take Q transpose times Q, I'll get the identity matrix. I know that because I did that proof over here. We could also check it, right? If I take Q transpose times Q, Q transpose is the row vector, 1, 0, 0, right? And I need to multiply that by the column vector. So this is Q transpose Q. That gives us the 1 by 1 identity matrix 1. Right, which is a little trippy. If I do it the other way, so if I do Q times Q transpose, I'm going to get the 1, 0, 0 vector times the 1, 0, 0 row vector. And now instead of taking a dot product, you're taking an outer product, right? You guys recognize that?
So you end up with a 3 by 3 matrix, the one in the corner and the rest here.
Yep, exactly. So I will end up with the, oops, that's not good. I will end up with the 3 by 3 matrix that looks a little bit like the identity. I'm gonna have a 1 up here. Unfortunately, it isn't the identity because everything else is zeros. With me on that? So, I can project onto an orthonormal set of vectors a bit easier than I can project onto a linearly independent one. You guys see that? That means it's going to pay off for me to have a way to come up with linearly independent sets, or to take linearly independent sets of vectors and turn them into orthonormal sets. You guys with me on that? That's going to be our last thing.